thank you everybody for joining. Got a lot of content to get through, so we'll get moving. So we're going to talk about GraphRAG, and not just the basically GraphRAG as a way of interacting and asking questions of with LLMs, but understanding how we actually generate the graph required to it. So let's start off with a little primer, or as I like to say it, arguing of robots. So LLMs. I'm sure we've all played around or tested with them at this point. Good thing to remember about them is that they're a probabilistic model that wants to please you. It basically wants to do it'll give you something that you'll be happy with, and that's the way they've been trained. So it's kind of like a parrot that has been given crackers over time, and you always give it a cracker when it says back to you that Polly wants a cracker. But if you train it that its name is actually its name is Polly, but you decided to train it to say Michael wants a cracker, it's going to give you wrong results back. And this is, it basically will do anything it can to get a cracker out of you. But the problem with that is that, especially when you're looking for truth, or if you don't want hallucinations, it causes a problem. So this is where a technique has come in called Retrieval Augmented Generation, or RAG, the second part of GraphRAG that we were just mentioning. This is where we essentially implement a smart search, which is the idea we're asking a question rather than going directly through to the LLM, where our question is used to determine from a sort of data set that we have behind the scenes, which is normally a private knowledge base of some sort, which a number of different articles. We basically use that to be able to pull back and actually show that data from basically retrieve just the stuff that's relevant to the actual query that we're putting in the first place. And then we pass that back to the LLM and get it to compile those results back together into a very human-looking response. Now, when we talk about GraphRAG, that's going a step further. And then instead of just returning these articles, it's also returning the articles, but then all the metadata linking them all together. So understanding that while the query I've asked is about this particular article about, say, Stephen Mc Gowan, but there's another article somewhere else talking about sailing, which is a sport that I enjoy, and somewhere that mentions me. So therefore, we understand in that knowledge graph sits behind the scenes that Stephen is interested in sailing, even if it doesn't say it in the article was retrieved. What that allows us to do is give a much more nuanced, much more contextual answer back when the LLM processes that into a full answer. Now, moving on from those concepts, last year I spoke about a knowledge graph that we had, and in Reality Logic we still have. This is what we call a logic graph. It's a logic knowledge graph. So it's basically, this is everything you would hit if you were to walk into a bank in Australia today and say, hi, I'd like to get a mortgage. This is 19 different source pieces of legislation, 138 different sections across all of those different pieces of legislation. And there's 987 different questions you can ask this. What this had allowed us to do, and we built it from a domain-specific language that came out of 20 years of research out of the National Science Agency in Australia. And what this has allowed us to do is to basically create a logic graph, understanding what are the type of questions you can ask all these different pieces of legislation, and then also what's the relevant data, the data that's required for you to be able to answer and evaluate against those questions. And it also ties back each of those piece of data and questions to where and what sections of piece of legislation it came from. So this was the original knowledge graph we sort of built as a company before LLMs and everything else has come along. And what I'm going to talk about today is different ways we've continued to enhance and build on top of this knowledge graph, add more nuance and context to our knowledge graph over time to improve what we can do with it. So, how do we use LLMs with knowledge graphs? Well, there's two ways. One which we've just kind of talked about, which is GraphRAG. Basically, we have a knowledge graph and we want to extract that information out of the graph. But one of the big problems of that is you need to have a graph in the first place. So how do we do that? So we can use LLMs to extract or pull data out of source documents and use that to build and expand capability within our graph. And then for those chunks of information or those articles or whatever it is, we can continue to do analysis and pull different information and so on out of these graphs as well, and build more nuance and context. Now, for anywhere that we talk about sort of enhancing knowledge graphs with LLMs, there's a sliding sort of capability of different things we can do. So we have sort of generic capabilities, and then to be things that are very domain specific. So there's some interesting tools out there that are going to be quite generic about how to sort of process any type of document, but I'll talk a little bit more about our problem space in a minute. But we have some very domain specific capabilities, especially that we've gone into, because we know so much more about our data and the types of data we have. So Rialto Logic's problem spaces, we deal with regulatory documents, whether that's acts of parliament, treaties, standards. Basically, while documents are normally referred to as unstructured information, our documents, while they are kind of unstructured and while the structure varies quite wildly, there is some implied structure there. For instance, there's a table of contents for pretty much every document we ever deal with. We take a document like this, which is the Biosecurity Act for Queensland from 2014. And for each of the documents we process, we would create, for instance, a document node in our database. And then we start to break down the hierarchy of the document. So, for instance, for this extract from the table of contents, we can see that there's part 1, 2, 3, and 4. So we end up with nodes for them. And then within the hierarchy, we end up creating then sections under those parts. I haven't fully put down exactly the same amount as in the table of contents here because it'll get unwieldy very quickly. And then we can see for part 4 has 2 divisions. So we created 2 divisions there, which we can have the sections underneath those. What this allows us to do is we have quite a structure to extract from the document. We've also gone down into, I suppose, the nth degree with this. Basically, every single paragraph in our document that we process is addressable. We understand where it sits within that hierarchy, and we'll see why that matters in a minute. So this gives us a kind of good basis to jump off from. So from here, we are then able to use a number of different LLM-driven techniques to basically analyze and add additional information around this sort of hierarchy of a graph that matters to us. So some of the things we can do, for instance, we could do analysis of part 1 and try to extract summaries or topics from that. And again, for each of the parts, we could do that at a section level as well, or at the division level. We can also generate vector embeddings, so we can understand if there's, when we're doing sort of semantic lookups, we can say, okay, I want to know about a particular topic or a particular sort of area. I want to understand if something semantically matches the question I'm looking into. And again, we can do those at part level, we can do them at section levels, and we do actually do them at all the different sort of levels that you see here. All of the blue nodes would have embedded vector embeddings as part of all these nodes. And then we can also look at 2 things that I'm going to dig into in a little more detail. One, which is building references. So each of these sections will refer to other sections and will also refer to other documents potentially. So doing that analysis and building out those relationships in our graph. And we'll see why that also gives us a lot of benefit later. And then we can also, where we talked about building that previous graph, that logic graph, that was all built by hand, where we were essentially writing a domain-specific language coding alongside the legislation. We'll see some examples in a minute, but we can also use some techniques here for generating that logic code to help us actually build out that logic graph on top of this graph as well. So basically expanding and adding more capability to our knowledge graph. So let's look at a real example of this. So this is 3 separate documents that have been ingested, and you can see we've extracted a deep hierarchy where every paragraph is individually addressable. Now, documents like these are meaningless by themselves. This is, as far as I remember, is the Export Control Act, the meat products regulations, rules related to that Export Control Act, and then the Australian Meat Standard. So all 3 of these documents need to be read together to make any sense between them. If you read something that's in the Export Control Act, you're missing all the context if you actually care about meat or meat exports, and you still need the industry standard as well to really understand that because they all refer to each other. Now, how do we get those relationships? How do we actually build those relationships between all the light blue nodes you can see here so we can understand how they talk about each other? So you need to build out a document ingestion pipeline. This is a simplified view of what we do, but essentially you're uploading documents, parsing documents, then processing them into this sort of graph you've just seen. But the part we're going to dig into in a little more detail here is looking at how we extract references, which is where we use a small language model. Something that's a simpler sort of trained model for extracting references. So this is like, I want to look at every paragraph and say, does this paragraph refer to another paragraph? And if so, give me that entity. So is there something that says like section 2 of the Act, or says section 32 of this instrument, something along those lines. From those, we then pass them through an LLM using few-shot learning, which is, I'll show some examples of how that works in a second. What that allows us to do is to generate a Cypher query to basically create the relationship between the source paragraph that refers to it and the place it's trying to speak about. And then we run those through and actually run all of those queries and generate the resulting graph. So we talk about few-shot learning. That basically means we create a bunch of examples. So we basically create, so here is some Cypher queries. Here is the comment on line 73 you can see there. That's basically the input that is found in a document. So subsection 211 or 2 of this instrument. And then here's the query that we'd use to find what that's pointing at and point at it. And here's some other examples. Now, this can be quite powerful, and we'll see here in a second what this results in. So this is only looking at the external references. So this is basically these same 3 documents we showed earlier, and here's how each different paragraph throughout these documents is talking about other places in the other 3 documents. This is what allows us to say, okay, when I'm reading this paragraph or this section, what's all the context that's relevant to this? So we use this few-shot learning pass-through LLM with those samples we showed before to help it generate these sort of these queries that allows generate these relationships and to kind of further expand our knowledge graph. Now, if anybody has actually done any testing with few-shot learning, one of the things you'll find pretty quickly is it works great when you have a minimal amount of variance in the type of queries you need to write. If you end up having to give it 100 examples to get it to understand how to generate queries for your problem space, you're going to very quickly lose efficiency. In my experience, if you have to give it more than about 10 examples, it's probably starting to get diminishing returns. That leads us to something else, and that's something that's probably really unique to kind of the structure we have. And it's, I don't really have a term for this technique, so I've given it a name, calling it target similarity generation. What this is allowing us to do is, when I said we want to be able to generate that sort of logic code that we're building alongside each section throughout the documents, that is what we're doing here. So there's a technique that's mainly used for training embedding models called target similarity tuning. This is somewhat inspired from that. What this is doing here is it's saying, okay, I have a section here that I have, and I will show some examples of this in a minute. I've got a section here that I have previously written code for, and this section looks like a section I want to now generate code for. So instead of having a fixed set of few shots or fixed examples, we're saying, okay, give me the top 10 examples, or give me the top 10 code examples that come from sections I've already coded against. And when we do that, we're sort of dynamically creating those few shots and using that to generate code, and then passing it through a compiler step, where we're basically running it through a compiler, seeing if it works. If it doesn't, pass it back and getting the model basically to continue to try and fix any issues in its code until it generates actual code at the end. This has been quite powerful, especially for, I suppose, quite a wider range of coding examples that we need to pass through. And for things that are a lot more complex, like what we're trying to code with this logic, it works far better than the few shot learning type of example we've used before. To show an example of this, 1 second. So here is an example of basically so section 30 is something that we've generated some code for, and here's that code that's been generated within our logic language called turnip. And we have the code generated here, but we can also see in kind of the data that we get back and store on our side is what has actually been, what were the actual samples that were used for generating that. So you can see here's the 10 samples that are passed to it. And we can see them here. So here's one of the samples that was provided for us. So here's like section 20 from the Export Control Act, which is from the same act that this one is from. And the second example is 40SF from the Electricity Industry Act from 2000. So coming from quite different areas, but the algorithm we've used to basically compare and see if this section is similar has identified that it has similarities, and it is used, the code examples came from it to actually use as a basis for what we pass back to the LLM to help it actually generate code in the first place. So we found this to be quite a powerful method to actually create code. I've jokingly called it, rather than target similarity generation, it's kind of like how a junior developer or kind of intern, first year grad, potentially developer all the time works, where they are working from previous code examples. They try to solve a problem by compiling, by bringing together different code examples to solve a problem, maybe looking at Stack Overflow, and then they compile, it breaks, compile, it breaks, compile, it breaks until they get a result that works, gets the answer they need, and that's what we're doing here. So quite a powerful technique for basically code generation. Why this works for us quite well is partially due to the structure of our data, because we have, like, one of the biggest issues if you're trying to build sort of code generation, or if you want to train a model for code generation or anything like that, is having well labeled code, because you're somewhat reliant on developers having labeled their code correctly, as in writing comments, which we're not known for. But also we are potentially, or we have to basically go and manually tag it. What we have here is, because we have such a tight link between here's the source that we're trying to write code for, and then here's any code that was written for it, we have a very close tie between what was the actual spec, I suppose, what we were trying to achieve and what the outcome was. So that's allowed us to create this sort of very interesting and then sort of new approach for how to do code generation, different to ones I've seen before this. So target similarity generation, I will probably do more talks on this particular methodology in the future. It's something we're kind of continuing to build and develop on top of. But yeah, I said it's something interesting, at least. Now, we've had two ways of enhancing a knowledge graph and building out additional capability in it. But let's talk a little bit about interrogating a knowledge graph. So this is where we talked more about sort of what, GraphRAG is a way of actually retrieving information and augmenting what's generated. So here I'll just show some examples of built on top of that knowledge graph we've just been talking about. So we've got a customer query. We use that to generate a query vector. So we say from the particular query that we're the question I have, let's go and find what are the semantically the closest links to it. And we also do some additional steps around extracting metadata. So for instance, because for us, key piece of metadata is jurisdiction. Like, did you mention Australia, or did you mention Victoria, or did you mention New South Wales? So we extract that and use that as part of the additional filtering and sorting on the data. And then use the vectors and the metadata to extract the results from our vector index within Neo4j, and then filter and sort that, returning the results, building out a references object I'll show you in a second. And then that's what we pass the LLM. It's got a structured, basically JSON response that it can then use to generate its textual responses. So if we go and have a look at a practical example of this, right. So this is more of a traditional RAG response. Let's look and see what happens when we're. So this is looking at an energy data set, looking at basically a lot of energy regulation. So what we can see here is that it's going and retrieving information from the graph, although in this particular scenario, because of some configuration I've got, it's not actually going and looking down into the graph. It's basically just saying, find me the top, basically 10 sections that match, I think it's actually top 5 sections that match my query that I've put in here. So find me the top 5 sections that match the what is a customer defined as question. So it's pulled back information from the National Energy Retail Law. And if we look, we can see some of that data, and we could drill down into it, but I won't too much for a moment. But what we can do is I can tell it to go, basically tell it to go 2 hops down from where it started. So it ended up, as I said, it pulled back particular references, and I want to tell it now to go from wherever those most likely places you found to answer my question in the graph. Now go 2 hops from there with the relevant information that I have from all that additional enhancement that you've made to the knowledge graph. We can ask the same question again. And what it will do now is it's going to, as I said, take those additional hops and get additional context to feed into the answer. And it uses that to create a much more contextual or augmented answer. So we can see here it's jumping down into some of the different sort of definitions, and I'll show a little bit of detail about that in a second. So if we look at basically the references that sit behind, this is like the raw data that it is extracted from the graph that it then using to actually generate the response below. But we now drill down into something like the National Energy Retail Law. We can see, as well as the textual information it got back from that section, it also has all the references. So we can see that there was a reference to a definition of customer, there's a reference to a definition of business premises, market offers, large customers, which are all terms that were used in here. And with that additional metadata, and again, we can drill down one more level again, with that additional metadata, it's able to generate a much more full response. And the last thing we can do is, from any of these references, we can jump to the source and see that in context as well. So here is section 5 of the NERL, which is the meaning of customer and associated terms. And we can see here is the references, which is what we said is basically and you can drill down into any references, which is going down further into the graph again. And you can even see that in context as well. So you can see for each of these, if we're starting basically at this section, and now we're trying to say what does that reference? They're referencing lots of different sections across lots of different, these red nodes are different sections across the act as well. So there's huge power to this, and it gives so much better context and gives much better answers as a result. That is most of what I wanted to show. So I will have a look and see if there's any questions anybody wants to answer in the last couple of minutes while we're here.